All right, so here we're going to work on our first analysis problem of the course. This is the rocket car problem. So we have this rocket car. It has a mass m. And at time equals 0, the car is stationary at a location s equals 0. And at that time t equals 0, the driver is going to release the parking brake. The car is going to start rolling down the hill. At some time later, I'll call it time TA, the driver flips a switch and turns on the rocket. And that rocket produces instantaneously a constant thrust force I call Ft. I'm going to assume that thrust force is rather large. So when the car starts rolling down the hill and you turn on that rocket is going to push hard enough to slow the car down, turn it around, and push it back up the hill again. So here's the deal. I'm going to give you the mass of the car, as I said, the angle of the road, that rocket thrust force, the time TA in which we turn on the rocket, and of course I'll give you gravitational field strength. What I want you to determine for me is the distance that the car travels downhill before turning around and heading back uphill again. Also, I want you to find the time at which it turns around, right? From the time at which it switches from going downhill to back uphill again. Now, as we work through analysis problems like this in our class, what I'm going to ask you to do is follow a set of rules, essentially a process that I call the problem-solving checklist. The problem-solving checklist has at least two objectives. One is to help you communicate your problem-solving process clearly so that you or I or one of your classmates can understand what you're thinking and how you're solving this problem more clearly. But also, it's hopefully here to help you think through the problem more clearly, to understand how the problems are structured, different types of problems are structured, and gives you a pathway to solve these sorts of problems. So again, this checklist is just a series of steps. The first one you'll notice is to make a sketch or drawing of the system being studied. And here's what I've got right here. I've got a drawing of my rocket car on the sloped road. The road is at an angle theta. I'm using the symbol S to denote how far the car has moved down that road. These things are already drawn for me in this problem, but I'm going to add more to this drawing just so I can keep track of quantities and have it sitting right here in front of me. Now, according to our checklist, the next thing we are supposed to do is list the quantities that are given in our problem. In this particular problem, there are no numbers given, and that will be customary for types of problems you see in this class. But we are given quantities. In fact, they're listed explicitly down here. We're given the mass of the car. We're given the angle of the road. We're given that thrust force. We're given the initial time that the thrusters turn on. And we're given the gravitational field strength. So these are our givens. So I'll go back to my paper right here. And again, this has to be listed explicitly. Now this last one, the gravitational field strength, the G, 9.81 newtons per kilogram, or 9.81 meter per second squared, however you want to think about this. This thing's always given to us. We'll assume that our problems occur on Earth, close to the surface of the Earth, so we don't have to sort of list it every single time, unless otherwise stated, of course. But so you don't have to list the G in my class, but it's no harm in doing so. So there's our list of givens. Then furthermore, the next thing we need to do is list the quantities that we are to find. All right, so go back over here. What I want to find. So one of the things we're asked to find is something I'll call TD, which is the time at which the car switches its direction, right? Before TD, it's heading down the hill. After TD, it's heading up the hill, right? At TD, it's switched from going downhill to uphill. Now, secondly, I want to find this other quantity I'm going to call D. That's the total distance the car travels downhill before turning around and heading back up again. All right, so there's that one. Number 4, we're supposed to list any assumptions that we're making. And really, I should just say non-obvious assumption. Right? We're usually going to ignore friction unless it's specifically in the problem. In this case, we have the rocket car has wheels that are going to be rolling. We'll assume that rolls without any frictional force to get in the way. So we can specify that or not. And likewise, we're going to neglect air resistance unless told to explicitly include it. And also, I'm not going to list that one either. But this other one, we had an assumption here that's spelled out in the problem, is that the thrust turns on instantaneously, right? As soon as the driver flips the switch, boom, you get the full amount of thrust right away. All right, so again, we'll go back to our problem-solving checklist for essentially a roadmap on how to solve these problems. So step number 5 says draw a free body diagram. I'm going to draw 2 diagrams, by the way, so let's be sure to label them. So I'll label my free body diagram FBD, like so. And usually you have to ask yourself, free body diagram of what? Sometimes there's a choice to make here. I think in this case it's pretty obvious. So I'm going to draw the free body diagram of the car itself. This doesn't have to be a beautiful picture, but it should be clear what you're drawing the free body diagram of. So this is my attempt at drawing the car. I don't know. There's the car. So what goes on the free body diagram? Free body diagram only has forces, right? So let's put on the forces here. So weight is acting straight downward. I've got a normal force. This is the force from the road pushing up on the cart, or I shouldn't say up, pushing on the car in a direction that's perpendicular to the surface of the road, hence the word normal. And then I had that rocket force too, right? So let's put the rocket force in. And that one's going to be tangent to the road. So there's my rocket force. I'll call the rocket force R. I think in a previous version of my notes I called it F, but F gets a little confusing sometimes. Now at some points, or at some times, the rocket force is 0. Other times it has magnitude Ft in the upward and to the left direction. I'm just going to call it R for now, but R during some intervals is actually 0. That way I don't have to draw 2 free body diagrams, I guess. Now in this particular problem we're going to be using Newton's second law, right? Newton's second law tells us that the sum of the forces, add them all up, equals mass times acceleration of the car in this case, right? The free body diagram is the left-hand side of the equation right here, right? What I'm also going to do, just sort of thinking ahead here, I want to represent the right-hand side of the equation diagrammatically as well, mass times acceleration. So if we go and look at our problem-solving checklist again, move up to item number 6, that says draw the mass acceleration diagram. Mass acceleration diagram is something I usually abbreviate MAD, like so. Again, it's a diagram of the car. So I'll draw a picture of the car again. For some reason this picture of the car looks a little bit different than the other car, but that's okay. It's the same body. And let's think about acceleration. What's acceleration? Well, remember, maybe I'll bring it up on this picture up here. Remember the position of the car is something I usually give the symbol R to. It's a vector. This is going to be S in the E hat 1 direction. Which way is E hat 1? I've sort of using it here, so maybe I should define it on my picture up here. So I'm going to use coordinates that are tangent and perpendicular to the track. So let me put a little coordinate axes on here like so. Another important use for our picture in step number 1 is so we can label things. So I'm going to call E hat 1 tangent to the track, or to the road, E hat 2 perpendicular to the road, like so. So therefore our position, I can represent the position of the car as a distance s. Remember there's the distance right here, s. The 0 point, s equals 0, is where we start off, right? And as the car moves downhill, s is getting larger, right? So position is an s in the E hat 1 direction. Velocity, call that v, it's just the time derivative of r, right? The only thing changing in this s e hat 1 for the position is the s. So we got this is going to be s dot e hat 1. And then the acceleration, this is what goes on the right hand side of our Newton's second law. Call that a. This is the time derivative of the velocity. Again, this is important to us because that's what's in Newton's second law. So I get a second time derivative of s and that acceleration. That's the definition of acceleration. Okay, so that is what goes in on our mass acceleration diagram over here. So our acceleration is just a vector that way, which I'll call ms double dot e hat 1, like so. Now I have a mass acceleration diagram. Alrighty, let's go back to our problem-solving checklist. We just drew the mass acceleration diagram. If you look at number 7 here, I'm going to actually skip number 7. We'll go directly to number 8. Number 8 says, state the physical principle that we're going to use. Physical principle, what does that mean? Well, so far in this class, the only thing we've discussed is Newton's second law. There's a physical principle that we're going to use on this problem. As the semester continues, we'll use the work-energy principle, we'll use the impulse-momentum principle, and various conservation principles that come from those two principles. And we'll also use Newton-Euler. And many problems will actually switch between principles. So it's important to keep track of which principle we're doing. Again, right now it's very simple, Newton's second law, but I want to state it explicitly. So I want us to come over here, and right here, Newton's second law. Of course, Newton's second law says you take all your forces, add them up, and this is just mass times acceleration. All right, so now an important part of Newton's second law is that it's a vector equation, right? I'm adding up all my forces together. Each one of these forces is a vector. And by the way, on this free body diagram, they should all be labeled as vectors, right? No scalars on my free body diagram, no scalars on my mass acceleration diagram. That's a vector as well. So the sum of these three vectors has to equal that vector. That's what Newton's second law says. But when we're actually trying to solve equations and stuff, it's easier to work with scalar equations rather than vector equations. So what I'm going to do is something you did in your statics class, but maybe you weren't as deliberate in expressing it this way, or at least thinking about it this way. We're going to break these vectors into components and then work with the components. All right, and I've already sort of described where I'm going to go with this. So we've got vectors, or basis vectors, e hat 1 and e hat 2, which are perpendicular and tangent to the roadway. So what I'm going to do is I'm going to express these vectors on my free body diagram, in my mass acceleration diagram, in terms of basis vectors e hat 1 and e hat 2. Okay, so that means we're going to decompose the vectors, and that's the step we skipped just a moment ago. Right? Go back to my problem-solving checklist. You see step number 7 says decompose vectors into components. Right? So that's why that was there. So this normal vector, for example, is going to be all in the e hat 2 direction. E hat 2 is, again, perpendicular to our roadway. It's normal to the roadway. And notice how I wrote this. So the normal vector itself, it's a vector. It has an arrow over it. And I'm saying this is equal to n in the e hat 2. So this n is a scalar n. So these two n's are different n's, right? Here's a scalar n, here's a vector n. They're different things. But the scalar n is, as I've written it, is the magnitude of the vector n. All right, the vector e hat 2 times the scalar n, that's a vector itself. So this is all consistent being a vector. The weight, let's think about that weight for a moment. Actually, let's go to the rocket force first. That's all in the e hat 1 direction. So I'm going to say this is r, a scalar r, e hat 1, like so. And maybe I'll say minus r, since this vector is in the minus e hat 1 direction like so. So therefore r, remember I said r at some times is going to be equal to 0, right? So maybe I'll write that down in here, so squeeze it in here. So r is going to be 0 if time is less than ta, right? Ta is the time at which the driver turns on the rocket. And I'll let this thing be what I call it. I called it Ft. There's our full rocket force, right? So it'll be Rft if t is greater than ta. You might say, what if t is equal to ta? Maybe I'll put this one 0 when it's less than or equal to ta. Cool, does that make sense? Okay, so that's the rocket, and then we need the weight, right? So the weight has a piece in the e hat 1 and a piece in the e hat 2 direction. So you should know how to decompose vectors into components right now. So I've got this weight. This weight, I've already quantities that I'd like to write vectors when I can in terms of quantities that are given. I just wrote, for example, the rocket force in terms of Ft, right? That's the quantity that was given to me when I listed up here. And now I got to do the weight. The weight is what? Well, I'm given the mass, and g, the gravitational field strength, is always given. So I'm going to write this weight in terms of m and g. So this is going to be mg sine theta in the I hat direction, and an mg cosine theta in the minus j hat direction. So it's getting a little bit crowded in here. Generally don't want to like these things to get too crowded. But maybe I'll do this to make sure that's separate. Cool. Got everything in terms of components. So what does that do for me? So now when I write Newton's second law, I can write it in terms of pieces, right? All these vectors have to add up to that vector right over there. But if I decompose these vectors into components, the e hat 1 and e hat 2, then all the e hat 1 components of the forces have to add up to the e hat 1 component of the acceleration. And likewise, all the e hat 2 component of the forces have to add up to the e hat 2 component of the acceleration. Right? So I split this thing up into pieces. So this first piece I'll call e hat 1. I'll put a colon right there. And then I'll just, if I drew my free body diagrams, mass acceleration diagrams correctly, then this should just be a matter of just reading directly off the diagram. So in the e hat 1 direction, oh boy, those weren't I and j, right? Those are e hat 1 and e hat 2. Mess that up. Hope you caught that. I just did. Okay, so now let's go e hat 1, e hat 2. So in the e hat 1 direction, I've got mg sine theta, and then I also have part of the rocket force. I'm just going to call this minus r, right? Minus r in the e hat 1. It's going to be 0 some of the time and ft on the other side of the time. So minus r. And there's no component of the normal force in the e hat 1 direction, so add 0. And this has to equal the e hat 1 component of mass times acceleration. So all of mass times acceleration is in the e hat 1 direction, so I'll just call this ms double dot. How do you like that? Right? And then e hat 2, let's do the same thing. Again, we'll go through this component by component. I've got an mg cosine theta minus mg cosine theta in the e hat 2 direction, and nothing from the rocket force, and then I got the normal force, right? Plus n in the e hat 2. Again, I'm not writing e hat 2 out here. What this means is I'm filtering out the e hat 2 component here, right? So in the e hat 2, I just have this n piece, right? And let's look at mass acceleration. How much mass times acceleration in the e hat 2 direction? None. It's all in the e hat 1, so I put a 0 right there. Okay, I'll call this equation number 1. I'll call that one equation number 2. All right, so let's think about where we are. So we started off with a description of the problem that can be written down in terms of sentences and maybe a picture. And then we turn that problem into a diagrammatic representation with our free body diagram, mass acceleration diagram. And then we use the diagrams to convert it to a series of equations, right? Mathematical expressions, and not just any old mathematical expressions, but these are scalar equations, right? By picking out the E hat 1 and the E hat 2 components, I've got algebraic equations. These are the types of equations that we can sort of manipulate and solve and know how to. You've been doing this since you were in middle school, right? So what? So what does this tell me? So equation number 1, for example, let me say that. What does that tell me? That tells me that, look at this, m and g are given. R is your rocket thrust, that's given, theta is given. So I know from equation number 1 here, I know what the acceleration is, right? So I can write s double dot equals, this is going to be g sine theta minus the rocket force, right? But the rocket force, or the thrust from the rocket, is 0 up until time ta. So this is it. This is my acceleration for t less than or equal to ta. And it is g sine theta minus ft over m for t bigger than ta, right? Like so. So here's what I get for acceleration. That's kind of cool. So that comes immediately from it. I can look at equation number 2 and I can find the normal force. Right, normal force is going to be mg cosine theta, but notice in my problem we're not asked to find the normal force. Since there's no friction in the problem, there's no dependence on the normal force anywhere. So I think this equation number 2 is just sort of there along for the ride. It doesn't really tell us much. The real important information comes from equation number 1. And here's where I get the acceleration. Now let's think about what we're going to do with this. Yeah, we got to think big picture here. Now we have to put the whole sort of problem into perspective. So let's go back to what we want to find again so we can think about where we're going with this. So remember, what we want to find is the time at which the car switches direction. What time does the car switch direction? And also want to find the distance the car travels downhill before it turns around. And here's where I'd like to pick up on previous work we did. Remember when we were making these plots, the plots of s and s dot and s double dot, all versus time. So if we can think about it in these terms, I think we can see exactly what's happening in the problem. So remember, what we do is we start with the s double dot, right? The s double dot, in fact, is what we were able to solve for in our equations of motion here, right? We found the s double dot for time up to time a. It says positive constant g sine theta, right? So here's s double dot, and for a while it's just g sine theta, which is some positive constant. Let's say up until this time right there, which I'm calling ta. And then at time ta, since the rocket thrust comes on instantaneously, I'm subtracting off this rocket thrust divided by the mass. Remember, the rocket thrust is sufficiently big to push the car up the hill, or push the rocket car up the hill, so it has to go negative. It has to jump down here at time ta, like so. So there's the s double dot. Right now, if I want the s dot, I just have to integrate. So remember, the rocket car starts off at 0 speed, so it has to start right there. And if s double dot is a positive constant, that means if s double dot's a positive constant, that means s dot has to be growing at a constant rate, like so, up until ta. We'll call this ta right there. Right, so s dot is growing up until ta, right? And then at time ta, s double dot becomes a negative constant, so therefore s dot after time ta has to decrease at a constant rate, like so. Yeah? And then S equations, well, think about that for a second. S starts off at 0. Remember, the car starts off at the top, S equals 0. And the rate of S is increasing. So rate of S, so S dot starts off at 0. S starts at 0. But since the rate is 0, this thing starts off flat. But as time goes on, this thing gets steeper and steeper, like so. S dot is the slope of S. So the slope starts off at 0. It's flat like so. And then the slope gets bigger and bigger as we go on. Okay. Why don't I just draw another vertical line about right there? So what happens to S now? I'm doing this quickly because we've already done this. S dot is still positive, so S is going to keep on increasing, right? S's rate of change is S dot, right? So S dot goes down to 0, so the rate of change of S, as it's growing, it gets smaller, like so. Yeah? And at this point right here, S dot goes to 0, so that's where S reaches its maximum. Boop, like so. And then beyond this time right here, S would be decreasing, like so. So again, this is really nice for our big picture view of what's happening, right? Because the thing we're supposed to find, where are we supposed to find two different things? Let me go down to the second one first. We're supposed to find the distance the car has traveled when the car reaches its lowest point. When the car reaches its lowest point, it's as far as possible away from the beginning point. Well, here is where it reaches the farthest possible away, right? Here's where it turns around and starts heading back uphill again. So if I were to draw another little faint line right there, that distance right there, that's D. That's what I want to find in the second part of the find, right? The first part of the find the time at which the car switches direction, right? The time it switches its direction is when, again, here's where it's going downhill, it reaches its lowest point, and then it goes up again. So here's the time, TD, that I want to find right there. TD, right there, that's where it reaches its lowest point, TD. That's where it switches its direction. Okay, so here's our big picture. So again, I've got a mathematical expression for these two accelerations. Now I need mathematical expression for this velocity and that position, right? If I can get velocity, the time at which it switches its direction, that's the time at which the velocity passes through 0 again, right? And if I can find position, what I need to do is find the position at that time TD. Ooh, nice. That's the big picture. Let's go for it. So now to get these expressions for velocity and acceleration, you might remember some so-called kinematics equations from physics. I'm going to suggest that you not use them. Yes, not use them. Because first of all, they're just things that you have to memorize. And I don't like just memorizing, because when students memorize these things, they often don't memorize the special conditions that have to be true in order for which it's valid to use them. So what I'm going to suggest you do instead is just do straightforward integration. Simple integration. S dot is always the integral of S double dot by definition. You don't have to remember anything else but except for that's the definition. To get from S dot to S, that's just integration, okay? That's just simplest, most elemental thing you can do. So let's do it that way, right? So I'm going to say find S dot. S dot is this component of velocity. Now, S dot is just the integral of S double dot. And remember, S double dot came in two different flavors depending upon whether your time is before this time you turn on the rocket or time equals after you turn on the rocket, right? So before you turn on the rocket, S double dot is just G sine theta. So I'll say for t less than Ta, S dot is just going to be the integral of G sine theta dt, like so, right? And the integral of that thing is what? what? The integral of sine is minus cosine, right? So minus g cosine theta. How does that look? Right? The integral of sine is minus cosine. Yeah, look good? No, there's a problem with this. Do you see the problem? The problem is, well, this is why when I integrate, by the way, some students aren't very careful here. When I do an integral, I'm always put in the variable you're integrating with respect to. We're integrating with respect to t here. We're integrating with respect to time. There is no time in the integrand, right? There's a theta, and theta is not changing in time. Theta is just a constant. So all of this, g sine theta, is just a constant. So the integral of a constant is just that constant times the t. So what I have here is g sine theta t. Yeah, there's the integral, right? And I've written this as an indefinite integral. So when you integrate, you also get this constant of integration, which I'll call C1. And again, this is valid from time equals 0 up through time ta inclusive. So now the question is, what are we going to do with this constant? That's just constant. You weren't given any constant here, right? Where's the constant? Well, the constant comes from the boundary condition, or in this case, the initial condition, right? We know that at time equals 0, s dot has to be 0, right? So I'm going to say initial condition, which I usually just abbreviate IC, is that s dot at t equals 0 is got to be 0, right? So what have we got? An expression for s dot here. S dot is g sine theta times t. Let me just put the 0 back in there. So this is going to be g sine theta times t, the time, but time, I'm looking at time equals 0, right? So times 0 plus c1 has to be 0. But g sine theta times 0 is 0 plus c1, that has to be 0. So this means that c1 has to be 0 in our case. Yeah, do you see how we fit that initial condition in? Call it a boundary condition, call it an initial condition. Yeah, so therefore s dot is equal to g sine theta, I'm looking at my expression up here again, plus c1, but c1 is 0, times t, c1 is 0, so this is what s dot is for 0 less than t, less than or equal to t, less than or equal to ta, right? So here's that expression for s dot. It's g sine theta is just some constant, right? So this is a linear function in t, it passes through 0. And that's exactly what we got up here. So let me do the other time interval. So let's consider what happens after time ta. Here's time ta, right? What's happening after time ta? Let's work out that one as well. So let's say for t bigger than ta, we've got s dot is equal to the integral of s double dot. But the integral of s double dot is now going to be g sine theta minus ft over m. So let me write that down. G sine theta minus ft over m. I'm integrating all of this with respect to t. This is going to give me g sine theta minus ft over m. Again, we're integrating with respect to t. This thrust was a constant thrust, so integrating it is very simple. If this was a non-constant thrust, then we'd have to take a little more effort. But in this case, it's really simple, right? And then I get another constant of integration that I'm going to call C2. Now here comes the question. How am I going to find this C2? Again, I find it through an initial condition or a boundary condition more generally, right? This is another sort of straight line right here. In fact, we're kind of expecting that to be a straight line. But the way we match the C2, this straight line out here has to match the other straight line we found earlier at time TA, right? So that's how we're going to get that C2, right? By matching these two curves at this location right there. Okay, so in order to match that, what we're going to have to do is figuring out what S dot was at time TA. So I'll call this one, let's see, I should call this one maybe equation number 3. So I'll say observe from 3, we got S dot at TA is equal to just G sine theta TA. And now I'll say that, let me get this in equation number 4. So we'll choose C2 so that equation number 4 matches 3 at t equals TA. How about that? Right? So that's describing what we need to do. By the way, when I work on this, I'm kind of expressing my thoughts on how this sort of works, right? I'm not doing this just because this is an instructional video and you want to describe it the first time you see it. I actually want, when you're working on this, I want you to lay out your thought process pretty much the same way. All right, so let's do it. I'm going to take equation number 4, which is right here. I'm going to stick t equals TA in there. So I've got S dot at TA is equal to, reading right from above, I got G times sine of theta times, minus F of t over M, all times TA, right there, plus C2, right? So there's equation number 4 with t equals TA substituted, and I have to match that to equation number 3 with t equals TA in there. So this is going to equal to G sine theta TA. Yeah, and notice on both sides, over here I have a G times sine theta times TA, and on the right hand side I have a G times sine theta times TA. So therefore this term is going to cancel out that term, and what I have left is, I'm just going to read it right off here, FT over M TA plus C2. Boom, boom, that's what's left there, and I've got nothing left on the right hand side, so that's 0, which tells me that C2 has to equal FT over M TA, right? I just solved for this constant of integration, which matches the boundary condition at time t equals TA. So therefore I take this value of C2, and let me just scoot it up here, take this value of C2, substitute it into my equation for T4, and I've got it, right? So here's S dot as a function of time, and I've got G sine theta minus FT over M, all times T plus FT over M times TA, right? So there's my equation for S dot for when T is, let's say, for T bigger than TA. Now let's think about what this means. This is your S dot when T is bigger than TA. Let's go back up here again. So here's our S dot. So this was equation number 3 for S dot. Here's equation number 4 for S dot when T is bigger than TA. Right? That's this thing right here. And we're really interested in this because remember what we need to find. We need to find when S dot goes to 0. This is where the rocket car, momentarily, just for an instant, stops and turns around and heads back uphill again, right? That's one of the things we want to find, and that's one thing we can find out right now. So say when t is equal to td, S dot is equal to 0. Yeah? That's the special case right up there. So let's do it. So let's say S dot evaluated at TD. TD is going to be bigger than TA, so we're going to use equation, this one right here for it. Maybe I'll give that a name. Call this one equation number 5. Right? So all I have to do is stick TD in there. So I got S dot is equal to G sine theta minus FT over M. I'm sticking TD in this thing now, plus FT over M TA, and that has to equal 0. Whew. Again, what I want to do is I want to find what TD is. There's TD. I've got an expression. Look at this expression. This is an expression where TD is the only unknown, right? Here's my givens again. I'm given M, I'm given theta, Ft, Ta, G, right? G is known, sine theta is known, Ft is known, M is known, TD is what I want to find out. Ft is known, M is known, Ta is known. Wow! Now I can solve for the TD. So TD is going to be equal to, look at this. How about I put this on the other side, so I got minus Ft over M Ta, all divided by G sine theta, minus Ft over M, like so, yeah? There's a TD. I'm thinking this is looking good. Let me just clean up a little bit. I think this answer is okay. It just makes me squirm a little bit to look at it with the minus sign on the top. So I'm expecting this TD, this is TD, right, to be positive. Let me I don't like that minus sign up top. So this is going to be the same as Ft over M Ta, and let's switch the order of this difference in the denominator. So let's call this Ft over M minus G sine theta, right? So essentially what I've done is I've multiplied both top and bottom by -1. I kind of like that a little bit better. Another thing I don't like about this is that there's an M in both sides. Again, this is just more cosmetic on my part. So let me just satisfy my own peccadillos here. I don't like having a fraction inside, a fraction within the fraction. So notice I can get rid of it. I can make this look better, at least in my mind, if I multiply both the numerator and the denominator by M. If I multiply the numerator by M, I've got Ft times Ta, right? Multiply the denominator by M, I've got Ft minus Mg sine theta. Yeah, I just like that so much better. All right, and that's my answer for TD. Okay, we're still not done yet, by the way. I've got an answer. Let's look at my problem-solving checklist again. So here's where I was supposed to be showing my work. I think I showed my work pretty well. It's quite a bit of work here. Let me scroll down. It says when I have an answer, I should put a box around the answer. Yes, absolutely. So whenever you have an answer, you should box it. You should tell me this is your answer. Okay, this is one of the answers. We actually asked for two things, but here's one of our answers. Right, I'm putting a box around it to indicate that this is my answer. Cool. Next thing in my problem-solving checklist, I should check the dimensions of my answer. Okay, this is really important because it says this time I picked out right here. What is that? It's just got a whole bunch of symbols here. That answer should make sense. This should convey meaning. And what I see is an alphabet soup. So, well, at the very least, the dimension should make sense. Okay, so on the left-hand side, what is this? This is the time where the rocket car turns around and starts heading back uphill, right? But most importantly, it is a time. So on the left-hand side of the equation, I have a time. On the right-hand side of this equation, this thing better be a time, right? Otherwise, it would make no sense at all. So let's look at this. I think the easiest way to do this is in terms of force, right? I'll just write dimensions here. In the numerator, I have a force times the time. And the denominator, what do I have? In the denominator, I have a force, right? That's the rocket car thrust. And I have an mg. Mg is the weight, right? Weight is a force minus a force times sine of theta. Sine of theta is just a fraction, right? It doesn't have any units associated with it. Yeah, so what this is a force. So in the denominator, I have a force. In the numerator, I have a force times a time. But notice this force will cancel that force and just leave a time. So that's cool. So I just checked my dimensions. Isn't that nice? And then finally, if we look at our problem-solving checklist, it says the answer should make sense. Yeah, does this answer make sense? Well, for one thing, you might want to check that this TD better be positive, right? You got to remember the car starts off at time equals 0 with 0 speed. So here's time equals 0 right here. So the place where the car goes back uphill again, first of all, it better be a positive number, yeah? And second of all, it better be a number that's bigger than TA, right? Otherwise, it wouldn't make sense. If we got a negative number for our answer, a negative value of time, that wouldn't make sense. That means it would turn around before we even started. And it better be TA, because it means we better start turning around after we turn on the rocket thruster, right? So we need this TD to be bigger than TA, and we need to be positive. All right, so let's check this out. First of all, is it positive? Well, the FT itself was positive, right? Let me make sense of that. Let's go back here. Here's the rocket force again. Rocket force was R in the minus E hat 1 direction. Minus E hat 1. Okay, so a positive value of Ft would correspond to a force pushing up the hill, right? So Ft is a positive number. Cool. And how about Ft minus mg sine theta? What's mg sine theta again? Ooh, here's mg sine theta. Mg sine theta is the tangential component of the weight. It's the component of the weight in the E hat 1 direction. Well, Ft is the component of the rocket force in the E hat 1 direction. And the rocket force in the E hat 1 direction has to be bigger than the weight in the E hat 1 direction. Otherwise, it would never slow down the rocket car. And it would never turn it around. So I need Ft to be bigger than mg sine theta. Since Ft is bigger than mg sine theta, this denominator is positive. And also, guess what? The numerator is positive. That's cool. So therefore, TD is positive, right? Okay. Is TD bigger than TA? Interesting. Notice here, write it on scratch paper right here, this answer that I get for TD. So notice this answer I'm getting for TD. What is that? It's some number, Ft, divided by another number, Ft minus mg sine theta, right? Times TA. I'm going to stick the TA out here, right? So I've got some fraction, if you will, times TA. Well, TD is going to be bigger than TA if this number right here that I have circled is bigger than 1. I need this to be bigger than 1, right? Well, is it bigger than 1? Yes, it is. Because here I have something in the numerator, Ft, and the something in the denominator is, again, it's something positive, but it's something smaller than Ft, right? It's Ft minus something positive. So I've got something in the numerator, which is bigger than something in the denominator, so this thing right here is bigger than 1. So therefore, that means TD is bigger than TA. Yeah, isn't that cool? So yeah, this answer is making sense. Now, in my checklist, this check that your answer makes sense. This is not something that I definitely need you. This is not something that I need you to write down on in your work. It's something you kind of do on the side. It doesn't have to be written here, so that's why I sort of wrote it on my own scratch paper. The unit check or the dimension check, I do want you to write it down. But checking it that your answer makes sense, that goes on your own. So I'm at a point where I'm rather confident that this is a good and valid answer. And I'm happy with it. All right, so before we wrap up the discussion on this problem, I want to show you where we've been, right? So recap where we've been. So first of all, what we did not do is try to squeeze our answer into the margin of some problem statement someplace. I took a whole 3 pages to write out this answer. Right? I took a whole 3 pages to work through the details, to communicate my thought process and to go through all the steps. So I started off by drawing a drawing of the problem and labeled relevant things. I listed my given quantities. I listed the quantities that I wanted to find. Actually, I only did half of it. I listed an assumption that we had, that the thrust turned on instantaneously. Then I went to a free body diagram. And after that, we did mass acceleration diagram. We did that because we're using Newton's second law to work out this problem. I set up, first of all, I went back here and I decomposed the vectors into components. So I set up my equations of motion by splitting up this vector principal into E hat 1 and E hat 2 components. So I get two scalar equations that I can solve. Only one of them was important to me. But I found an acceleration. Once I find an acceleration, I sort of looked at the big picture, thought about what did I need to do. I needed to integrate that acceleration to find a velocity, or component of velocity, I should say. I did it through direct integration, analytical integration of the symbolic expressions that I had, and manipulated things to match boundary conditions, right? When you do the integration, you get the constants of integration that you have to solve for by satisfying initial conditions or boundary conditions. I found an answer that I was looking for. I checked the dimensions of this thing. On the left-hand side, I had a time. On the right-hand side, I figured out that I also have a time. So that was good. And once I had some confidence in it, might not still be right, but I have some confidence in it. It made sense. I put a box around it so that I know that this is an answer. And look, it took me 3 pages to work this out. So don't try to squeeze this into some margin. Write it all out so that one can read it and one can make sense of it. All right, so where does that leave us? Remember, here's our problem. We were asked to find this time at which the car switches direction. We did that one. That one's done. Okay, now we have to find the distance the car travels downhill before turning around. I'm going to leave that one for you to do. Okay, that one's your task. Okay, but we've already discussed how we do it. In fact, we've done most of the work already. Right? What you're asked to, use this plot we created before, what you're asked to do is find this distance right here. So you're going to have to take our expressions for s dots. We're going to have to integrate them again, right? We're going to have to integrate the value of s dots when time is less than ta to get this curve right here. You're going to have to integrate the s dot for, oh, by the way, you're going to have to match this boundary condition too when t equals 0. And then you're going to have to integrate s dot for t bigger than ta. So you have to integrate this curve to get this one right there. Yeah, and you're going to have to choose a constant of integration to get a match right here. And then you're going to take that time that we just found and we're going to substitute it into the expression up here, and we're going to find the distance traveled at that time that we just found. All right? This one's up to you. I know you can do it. Go for it.